part. So the first thing that we need to do is I need to show you on your calculator where you can get a number cube. And some of you, if you don't have it, you'll have to just go with someone else's calculator. And you're going to roll dice. So on your calculator, I need you to go to right here, this button that says apps. So notice you can see what I pushed. And then I need to go down, and it's in alphabetical order, and I need to go down to probability simulation. So I'm going to push alpha P so that I can get down to the P's, and I'm going to go to probability simulation. So I am going to press any key, and then I am going to go to roll dice. But the thing that we're doing, if you look at this right here, we are trying to find the sum of two dice. So we want to roll two dice and add them together. So we got to tell our calculator to do that. So right here, I need to look at settings. And the one thing I need to do is I need to roll it 36 times. So when I come right here, instead of just rolling it once, I can roll it once and then sit there and count it, but I can just roll it 36 times if I want. I can tell my calculator, roll it 36 times. How many dice do I want? I want to roll two dice. How many sides do I want the dice to have? Do I want to store it in a table? Should I clear the table first? Yes. So that's the settings I'm going to use, and then I'm going to push OK, and it's going to roll two dice 36 times for me. Oh, I got to hit roll, and it will roll it for me. Okay, if you guys just push your arrows, it's going to tell you how many of each sum it rolled. So this is the different sums two dice can add to between 2 and 12. If I push the right arrow, it rolled a 2 0 times. It rolled a 3 2 times. And you can see it says on the top frequency. So on this one, it happened to roll a 7 9 times. That was the one that rolled the most. But at 8, it only rolled 2. So is what you need to do from there is whatever your data is, you need to put it in the frequency that it was rolled and then the probability it was rolled.
Are we doing the frequency of the 56?
Yeah. So like a 3 was rolled for me 2 times. So I'm going to say that the 2 was rolled 0 times. So the probability that I rolled a 2 on that set of numbers was 0 out of 36. Then this one was 2 times, so this was 2 out of 36 is the probability. And we could do a decimal fraction or percent. Let's just do a fraction. And you could reduce it if you wanted. It doesn't matter as long as you know that this is the probability that you rolled that number, or that sum of numbers. Okay, after you guys get done with that part, it says make a probability distribution for the sums of the numbers you rolled 36 times. Oh wait, we gotta do number 2. So number 2 says complete the graph using your data. So what's the probability on mine? I rolled a sum of 2, 0, so I don't do anything. What's the probability I rolled a sum of a 3? So you can see the numbers are kind of on the bottom. You can see some of them. My 3 was 2 out of 36. Looks like I'm making a bar graph of the probability going up. Okay, my 4 was only 2. You just continue on until you fill them all in. The theoretical probability, the reason they chose 36 was because if I roll, these are the possible ways this could happen. If I roll a 1 and a 1, I get a sum of 2. So this is the sum of them that I'm going to write down. So here's your 6 dice. This one's a 2, 3, 2 and 1 is 3, 2 and 1 is 3. So this is like the theoretical probability. 3 and 1 is 4. Notice how it keeps going like this, down the diagonals. probability of what we did. And that's where they're coming from, is just when you're adding these numbers together. So there's a probability of 2 out of 36 times that I would roll a sum of 11. 1 out of 36 times, theoretically, I would roll a 12.
So do we do that on number 3?
And that's number 3. You do the theoretical probabilities of rolling the different things. So 2 was 1, so you just kind of go between. 3 was 2. No, 3 was 2, yeah. And you just fill in that on number 3. And then answer the question to number 4, compare the graphs. Do you think the number of cubes you rolled are fair? So in other words, we didn't really actually roll dice, but do you think your calculator was fair and what it calculated is what it's saying? Could that be? And sometimes, you know, depending on what it happened to be, sometimes maybe you'll only roll like a couple 7s. Mine happens to like pretty much it goes up and down, kind of like the other one. But some of them, you know, just by chance, if it was only 36 times, maybe it's a little bit off. But if you do it 1,000 times, it's going to be very much like the theoretical one. Here, so when you get down to here, based on the theoretical probabilities, it's saying what's the probability of rolling a sum of 2 to 4? Well, you need to come up here and look and say the probability that I rolled a sum that's between 2 and 4 is, add these up, 6 out of 36. So you come down here and you write 6 out of 36. So there's a probability of 6 out of 36 that I rolled either a 2, 3, or 4. And then when you want to roll a 2 to a 6, then you have to also include in these numbers. So you want to add up, sorry, how many there are now. So you have to add up all of these and put it over 36. And then it says the probability of rolling anywhere from a 2 to an 8. So you go all the way, including all of these. A 2 to a 10, so you include them all. And a 2 to a 12. What's the probability you roll somewhere between a 2 and a 12? 36 out of 36, right? That's all you can roll. And that's the cumulative probability as you add them up. The sums as you go 2 all the way up to whatever the number is. So when you get done, this one is just saying to do it as a decimal, right? So what was, the first one was 6 out of 36. So someone tell me what 6 divided by 36 is. What? A 6, but what is that as a decimal? 0.16, repeating. Okay, so this one is going to be, you're doing it as a decimal as a percent rather than like a fraction. So still, this one is going to be a probability of 1 when you get done. On this first one, you need to complete, you do have to do the spinner one. You need to do all of these 1 through 10 is going to be the first part of your assignment. So on these first 2 pages, do 1 through 10. So I guess it's just your first page, right, because it's 2 to 1. It says, and it makes sense if you look at this first top part up here, the mean of a sample may or may not be the mean of the population, right? That makes sense. You have a population. When you do a sample, they may not have the same mean. The margin of error helps you find an interval in which the mean of the population is likely to be. So the margin of error is based on the size of the sample. So the bigger the sample, the smaller your margin of error, right? And it depends on how confident you want to be that it falls within that number. So right now we are only going to talk about being 95% confident. So if we want to be 95% confident that our mean in our sample is the same as the mean of the population, there's a certain formula for it. And it's based on the bell curve. This is a little bit different than we did with the normal distribution. We said that this was 68 and this was 13.5 when you went out 2 standard deviations. and this one's only going out 1.96. Okay? So when we look at 95% confidence, that means that the probability is 95%. So this is important. So listen, Cameron, put your phone up. You are 95% confident that the mean of the sample is the mean of the true population. So there's a chance that it's not, but if we take this margin of error and figure out where we want it to be, that we can be 95% confident. So right above, this is hard to see on your paper, so this is what the formula is that we're going to use to find the margin of error. So ME is standing for margin of error, that's right here. You take, and it's different if you want something besides 95% confident, but right now we're only being 95% confident that it's falling within this spot. You take S, which would be nice if they keep using the same thing, but S is standing for standard deviation, divided by the square root of n, where n is the number of numbers. Okay, so that is going to be our margin of error. So the bigger you have, like the bigger your sample size is, the smaller your margin of error is going to be because you're going to divide by bigger and bigger numbers. And it all depends on your standard deviation too. Because the smaller your standard deviation is, and the smaller your margin of error is going to be as well. We are going to talk about the confidence interval. So instead of just finding the margin of error, we're going to say, okay, this is actually the intervals that we're 95% sure it's going to fall somewhere within this interval. So you take, this is the, mu is the mean, and you have to take the average value and add the margin of error, and then you have to take the average value and subtract the margin of error. So right now is what I need you to do. I need you to put these numbers in because this is the wait time in a grocery store. A manager wanted to determine the wait times for customers in the express lanes. He timed customers chosen at random, and this was their wait time. So we need to find, in order to find what is the mean of standard deviation, so we've got to do that first. So put this in your calculator. You're going to do calculate one variable statistics, and you're going to find the mean and standard deviation, and we're going to find like the other stuff that goes with it up here, the margin of error and the confidence interval. So you've got to put all those numbers in. I don't know if you can see them good, or you can just look up here and put them in. So remember the standard deviation we want to use is this 1 omega. And this says round to the nearest tenth of a minute. So we're just going to have 1.8 is our standard deviation. And for our mean, so you guys tell me if you're at the same number. The mean was 5.36.
Yeah.
So this is saying on average the wait was 5.36 minutes with a standard deviation of 1.8 minutes. Okay, so that's what we did last time. At a 95% confidence level, what is the approximate margin of error? So now you are using your formula for margin of error, which is this one. You need to take 1.96, take the standard deviation, and divide it by the square root of the number of numbers.
So the S is standard deviation.
S is standard deviation. And I don't know, I would say to be more accurate, round it to the nearest tenth. So all we're doing is just really plugging in
26.
numbers. So this is saying we are 95% confident that this mean of 5.36 is correct within 0.6 minutes on either side. So that's our margin of error is 0.6. So if you want to know the confidence interval for 95%, that's asking you during which times, which spread of times between where to where are we 95% confident that the average wait time is somewhere between there. The actual mean wait time of the population instead of just our sample. Our sample is 5.36, but we need to find the other one. And this is the kind of question that it would ask you like later maybe on the SAGE test. It would say, here's the mean of 5.36. It has a standard deviation of 1.8, and hopefully they give you the margin of error because that's going to be a hard thing to memorize, right? Especially if this is only for 95%, and we only know this one formula. But if this is the margin of error, if I want to know the interval that it lies in, I have to take 5, I guess I was supposed to do it for 5.4, right? Not, so that's 5.4. If I have 5.4 and I add 0.6, I get 6 minutes. And if I take 5.4 and I subtract 0.6, I get 4.8 minutes. We are 95% sure that the actual average wait time was somewhere between 4.8 minutes to 6 minutes. I guess we should, if we did it like as interval notation, that would be what our average wait time is. If we're 95% sure the average wait time is somewhere in there. So, for example, if you know a sample proportion, so this is a sample proportion, it's kind of a weird thing, and this is what I've really heard it called. You can't really see it right there, but it's p-hat. Doesn't want to tie like a hat. That's what I've heard everyone talk about it. They say that's p-hat. So p-hat, if you have X number of times an event occurs and n is the number of the sample. So that's just like normal. Like I look at you guys and I say that 5 out of 32 people have a red shirt on. That would be a sample proportion. So that would be, I'm only polling my class, not the whole school. So it's still just some sort of fraction of what you think is happening. So this one, write the ratios of percents round to nearest tenth of a percent. If you had 1,085 voters and 564 favor candidate A, what is the sample proportion, and write the ratios of percents round to nearest tenth. So this is just going back to simple, what's the proportion of people who voted for candidate A? Okay, 564 over 1085, which rounded to 62 point what? So nearest tenth would be 5. 52. Sorry. 52.5.
That's what I got right there. I'm just like pussy please.
52.0. Okay. And I can let you do this other one. Point is tossed 40 times, this many heads. This is what we need to do is come up with this part though. The margin of error for this, so this is different because we don't have a list of numbers. The other one is when we have a list of numbers, we can find the mean and standard deviation. This one is just a sample proportion, so you have your sample proportion. If you want it to be 95% confident level, this is the formula you need to use for the margin of error. So you have to do, and it's kind of looks hard to plug in, but if you store things appropriately, it's not going to be too bad. So if I were you, if I were finding the margin of error of this, I would store this number as a variable because it's going to go right there. And then, if I were you, I would also, can you guys see what it is then? It's 1.96, we got our 95%, square root p hat 1 minus p hat over n. To put this in easily, once you do your 564 over 1085, oh, and the thing, that you're doing right here, you need to do this as a decimal, not a percent. So you don't want to put in 52%. You want to put in this fraction right here, or the decimal that's equivalent to that fraction. So you want to make sure that you're not putting in a percent, you're putting in a decimal. So the easiest way to do it is to store that to x, or I guess mine's a t because I must be in parametric mode. And then when you go to put it in, put in a fraction button. That's the best way on these calculators. So when you go to do it, put in your fraction right here, alpha, is it F1 fraction? Then it's going to be super easy to put it in and do p hat 1 minus p hat over n. Okay? And since I stored it, it will be really easy to put in. If not, it's a nightmare with all the parentheses. And the number of numbers was 1085. Yeah.
How do you do the fraction thing on the calculator?
The fraction button is alpha F1.
Oh, F1.
Yep. Then it makes it so much easier. Did you have to find it for that one or not?
No, you don't have to find a balance.
Okay, so this one, the margin of error was 3% pretty much, right? 3.0%. That's our margin of error. So we had 52% voted for candidate A with a margin of error of 3%. So it could actually be, we're 95% confident that it's somewhere between 49 and 55% based on our margin of error, which has to do with the proportion, and really it mostly has to do with the number of people that you survey. The more people you survey, the smaller your margin of error is. Here, on this one, my margin of error was 3%. My confidence interval, so these were just the numbers, not the percents, the kilos. Inside your formula. Oh. I don't know. As long as you say what it is, like percents, I don't know. It would be 49 to 55%. Percents would be fine. The main thing is you just realize what it means, right? So this was my margin of error. This was my confidence interval when I add it to both sides. So now you guys need to take a minute and do it for, I need you to do 1 through, so this next part is, it has to do with this down here. So right here it says drawing conclusions from samples. It has the z-score. So I don't know if you can see this very good. The z-score is, you take the data point, which is x is the data point. You take the mean of the population and you divide it by the standard deviation. So that's the z-score. So what the z-score is it tells you basically, and you probably could have got that formula on your own, it tells you how many standard deviations the number is from the middle, from the mean. So when we go right here, if we want to find the z-score of a newborn baby, the mean is big it. What is the z-score of a baby weighing 2,500 grams? We just need to take our 2,500 grams, subtract our 3250, our mean, and divide it by the standard deviation of 500. So someone hurry and plug that in your calculator, and that'll tell you the z-score of a baby that weighs 2,500. So negative 1.5, that's saying if this is where all the babies, the mean is 3250, if you go over negative 1.5 standard deviations right here to 2,500, that's how far away from the mean you have to go. It's negative 1.5 standard deviations to the left. It's going to be that one. So this one, you want to know how far you have to go to find 4,500 minus the average divided by 500. That'll tell you how far to the right you need to go, how many standard deviations that this 4,500 gram baby is going to weigh from the mean, where they're at. This next one, so you only have to do 1 through 4 on this one.
And where do we get the numbers for what we have to do?
So you had to do 1 to 10 on the first one, 1 to 9, and then 1 to 4. Okay, on this one, if I can find out where this is at, 22,700, I can figure out what percents they are, because I have my different percents right here. So it's probably going to be something right here. Like if I want to find the z-score of 2270, if you guys do this one, it tells you negative 1.96. So that's putting this baby right here, if it was 2270. Is that what it is? Yes? So it's right here. And if you do this one, 4230 minus 3250 over 500, that's this one right here. It ends up being 1.96. So the probability that a newborn baby weighs between this z-score and this z-score, they're right on them, then I can just look right here now at the percents, which is nice because it did. It's right on there. If not, remember we have that normal CDF, and I could put in 2270, 4230, put in the mean and the standard deviation, and it would tell me the percent of them that fell between there as well.
Are we going to use the same z-score formula for number 4?
Yes, it's very similar. Number 4, we can try number 4, try to do number 4, and if not, we can look at that in class next time. So look through it. It does talk about the z-score. And actually, if you guys want to look at 4 through 7, you can get some bonus points on this one. Because it is, you really do need to do the rest of it for it to make sense of why I was trying to do.